The first section is about the inductive and deductive reasoning. Inductive reasoning is the process of arriving at a general conclusion based on the observations of specific examples. Now we have actually two definitions before we can use the inductive reasoning. Conjective hypothesis. Now this is the conclusion formed as a result of inductive reasoning, which may or may not be true. So you may come up with a hypothesis about something, but that doesn't mean that it is true unless it is proven. The counterexample. This is a case for which the conjecture, the hypothesis, is not true, which proves the conjecture is false. So if you can just find one example in which the hypothesis is not true or the conjecture is not true, then you can use that as a proof to show that the conjecture is false. Now we have two different types of inductive arguments: a strong conductive argument and a weak inductive argument. Now let's take a look at this example. In a random sample of 380,000 freshmen at 772 4-year colleges, 25% said that they frequently came to class without completing readings or the assignments. We can conclude that there is a 95% probability that between 24.84% and 25.25% of all the college freshmen frequently come to class unprepared. Okay, so we call this technique is a random sampling. We'll discuss this more in chapter 12. Now, each member of the group has an equal chance of being chosen. So that is just random sampling. That means every person has an equal chance of being selected. And we can make the predictions based on the random sample of the entire population. Now, the reason that I call this is a strong inductive argument because we base on a random sample of a lot of freshmen, 380,000. This is a lot of people, and we know that we took the survey for 772 colleges. So this is a huge amount of schools with a large number of students. So after we make the conclusion based on the observations, we can see that this has a strong conclusion, a strong inductive argument. Comparing to the weak inductive argument from this example, we say that men have difficulty expressing their feelings. Neither my dad nor my boyfriend ever cry in front of me. Now, this person make a conclusion just by looking at two cases, her dad and her boyfriend. So we only have two people, and she make the conclusion just by having two observations. So it's very, very weak. Comparing to the last example, we have a lot of people, and we make the conclusion from a large amount of the data, a large amount of observations. Comparing to, in this case, only two observations. It's very weak in this case. So make sure the sample is random and it has a large population in order for you to make a strong conclusion. Okay, we have another example. Identify a pattern in each list of numbers. Then use this pattern to find the next number. We see that in order for you to go from 3 to number 12, we have to add 9 more, right? 3 add to 9 to get 12. And in order for 12 to go to 21, again, we have to add 9 more. And in order for 21 to go to 30, we have to add 9 more. And from 30, go to 39. Again, we have to add 9 more. So we see that the common difference between each pair is 9. Therefore, in order for you to get to the next number, you just have to add 9 more. And therefore, we add 9 more to 39, which gives me 48. The same thing in this case, we also using the inductive reasoning, but in this case, because the numbers are increasing quickly, so we cannot add a number to get to the next value. But now, because this is a quick increasing, we can try to multiply. So 3 go to 12, we have to multiply by 4. 12 go to 48, we have to multiply by 4. And 48 go to 192, we multiply by 4, and so on. So we know that the common ratio between each pair is 4. So in order for this number to go to the next number, we multiply by 4, which gives me 3072. Now, we can have another example using the inductive reasoning. So what comes next in this list of numbers? 1, 1, 2, 3, 5, 8, 13, and 21. Now, this pattern is formed by adding the previous two numbers to get to the next value. So in order for you to get to this value, 2, we add the last two numbers, 1 and 1 give me 2. In order for me to get number 3, I add the previous two values, 1 and 2 give me 3. In order for me to get 5, I add the last 2, 3 and 2 give me 5. To get 8, I add the last 2. And so on. And therefore, to get me the next number here, I add 13 and 21 together, give me 34. So different ways of getting the next number. You can add, you can subtract, you can divide, multiply, or even add the previous two values. How about this one? 2, 4. What is next? Now, this question is not giving you enough info, enough data for you to make the conclusion. Because in order to go from 2 to 4, we can add 2 to get to 4. Or we can multiply by 2 to get to 4. So, we don't know. We don't know which one is the correct way. Because it only gives you two values. And it asks you to predict the next one. In this case, we cannot really make a correct solution. Because it could be anything. So there could be more than one solution in this case. Because we don't have enough points, enough data. We need to know one more number to decide the correct pattern. Okay. This example is a figure. It gives you a figure, a sequence of a figure, and they ask you to decide what should be the next one. Now we know that we begin with a circle. We move to square. We go back to circle. We move to square. So the next one we know that it should be a circle, right? It should be a circle. And we know that if that is a circle, we can see that the next one will be a circle. But how do we draw the dots here? Now, we can predict that the dots will follow the patterns from 0 to 3 dots in a section, with them rotating counterclockwise. Okay? So we can see here, the 3 dot stay here, the 2 dot, the 1 dot. In the next figure, the 1 dot rotate counterclockwise, move here, the 2 dot move up here. In the next figure, the 3 dot move here. The next figure, the 1 dot here move to the next one, rotate to the next one counterclockwise. The 2 dots go up, and then the 3 dot go up here. And let's keep going on. So now the next one, the 1 dot we move up here in the circle, the 2 dot we move down here in the circle, and the 3 dots we move to the left side. And that is the next figure. The next objective is the deductive reasoning. Deductive reasoning is the process of proving a specific conclusion from one or more general statements. A conclusion that is proved to be true by deductive reasoning is called a theorem. Now in this example, we are using the inductive and deductive reasoning. So using inductive reasoning, apply the rules to specific numbers. And do you see a pattern here? So we can have any number here, 4, 7, and 11. Now, the first step is we multiply the number by 6. So we take odd number, we multiply it by 6. And then we add 8 to the product. So we add 8 to all the values. And then divide by this number by 2. Right, that's like 50 divided by 2, 32 divided by 2 give me 16, and so on. And then I subtract 4 from the quotient I just got. And then I got the final value. Now, do you see the pattern from here? From 4, go up to 12. From 7, go up to 21. 11, go up to 33. Any pattern here? Yes, we do have that. 4 times 3 give me 12. 7 times 3 give me 21. 11 times 3 give me 33. So from the beginning numbers, we all multiply by 3 to get to the final answer. And that is the result of all the steps here. Now using the deductive reasoning, we use any instead of using any number, we use the letter n, the variable n, to represent the number. And then we follow the step again. Multiply by 6, add 8, divide, and subtract. So I use n as just to represent the number. I multiply by 6, so 6n. I add 8, right? And then I divide by 2. And then we can simplify, we can split the fraction. And we get this 3n plus 4. Because 6 divided by 2 gives me 3. And then I subtract 4 from the quotient, the last step here. And it's equal to 3n. So from n, go to the final result is 3n. So that's why we know that we have to multiply by 3 from the beginning to the end. So we prove that, right? So we use the deductive reasoning to prove that the beginning go to the end is by multiplying by 3, just by this step. And this is true for all the numbers. N could be anything. So that's the end of 1.1. The next section is 2.1, the basic set concept. A set is a collection of objects whose the contents can be clearly determined. Elements or members are the objects inside a set. Now a set must be well-defined, meaning that its contents can be clearly determined. And then the order in which the elements of the set are listed is not important. So you can have the first member first, or the second member, or the third one, doesn't matter. The methods of representing the sets. Now we use the capital letters to name the set. A word description can also be used to represent the set. Now use the W to represent the set of the days of the week. So we use the roster method. The roster method is the equal sign, and then we open the bracket, and then we close that, and then all the set member have the comma in between. So W represent the set of all the days. So W equal open the bracket, Monday, comma, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And these are the days in the week. Sorry, it's the braces, not the bracket. Okay, the bracket is the square. The square, not the braces. This is the curly brackets. We can call that the curly brackets. So we use the curly brackets or braces to include the member of the set. We can also use the word description of the set. For example, this P equal, this set has Washington, Adams, Jefferson, Madison, and Monroe. This is the first 5 presidents of the United States. So this set represents the first 5 presidents of the United States. Another example. So write using the roster method. Set C is a set of the US coins with a value of less than $1, and then express this set using the roster method. So we use the roster method. C equal open curly bracket. Now any coin less than $1 is a penny, nickel, the dime, the quarter, and the $half. So we separate them by the comma. We write the name of the coin with the value of less than $1. Now that's another notation, which is the set builder notation. Now we can use the set W equal the X, and then the vertical dash X is the day of the week. So instead of writing W equal Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, we can use the set builder notation. We let X is the elements or all the element of X, and we use the vertical bar. This stands for such that, the word such that. So all the elements of X such that X is a day of the week. So it must be Monday to Saturday. Okay, so basically this one is the condition for the element of the set. It has to be a day of the week, and the first the variable before the vertical dash represent for any element in general. Now we can convert the set builder notation to roster notation. Okay, so A equal X, and this is the condition. X is a month that begins with the letter M. So we can have March or May, because March and May, they both start with the letter M. So this is the roster notation. This is the set builder notation. So in this case, maybe the roster notation is faster to write, because you just have to write March and May, 2 things, and that's all. Or you have to use the set builder notation and write X dash such that X is a month that begins with the letter M. But for all the example, the set builder notation may be convenient because if there are too many elements to write out in the roster form, then the set builder notation is better. The empty set is also called the no set. It's a set that contains no elements, so nothing is inside. So we have two different ways to represent the empty set: open and close curly brackets. So nothing inside to represent the empty set or the no set. Or you can use the big letter O and then with the dash here to represent the empty set. For example, the set of all the numbers less than 4 and bigger than 10. Okay, we want a number that is less than 4. And if that number is less than 4, there's no way it can be bigger than 10. So this number does not exist. So no element that is satisfied for this requirement. So this is the empty set or the no set. Okay, let's try to recognize the empty set. This is not the empty set. This is a set with one element inside, and that element is number 0. Now, this is a number. This is not a set. A set must be something inside the curly brackets. How about this one? X such that X is a number less than 4 or bigger than 10. Is this the empty set? Nope, because we have the OR. So if something is less than 4, maybe 3, right? Or bigger than 10, maybe 11 it's alright. So because this condition has the OR, so you can have a number less than 4 or another one bigger than 10, which is 11. So we do have something inside this set. So this is not the empty set. How about the next one? X such that X is a square. Remember the vertical bar here stand for the empty set. Okay, the vertical bar right here. Sorry, the vertical bar stands for the such that. So X, the element of X such that X is a square with 3 sides. We know that the square it has to be 4 sides. Right, the square 1, 2, 3, 4. If you call that a square, it already has 4 sides. So there's no way you can have a square with 3 sides. So there's no element inside this set. So yes, this is the empty set. Notations for the set membership. We have two different notations. The one with and without the dash. Okay, so this notation here is used to indicate that an object belongs to a set. So in other words, something is an element of the set, and this one represents something is not an element of the set. Okay, so for example, decide whether each statement is true or false. We know that this set contains all the letters from A, B, C to Z. So the letter R belongs to this set. That is true. So that's why it's true. Now, this set here has only number 1, 2, 3, 4, 5. So no 6, no 7. So 7 does not belong to this set. It's also true. How about this one? Well, this is not a single element. This is a set. And this is another set. So set A is a set, and the set A is not an element inside the set of A and B. So this is false. We can also have the set of natural numbers. Now recall from algebra, the set of natural numbers. Natural numbers are the number from 1, 2, 3, 4, 5, and so on. The counting number. So the 3 dots means there's no final element, and the list just goes on forever. Now express each of the following sets using the roster method. Set A is a set of natural number less than 5. So the roster method has the open curly bracket, the closed curly bracket, and the elements are inside with the comma in between. So anything less than 5, any natural number less than 5. Remember, natural number stack with number 1. So we go from 1, 2, 3, 4. We don't want to include 5 because we want something less than 5. So that is the set of A. B is a set of natural number greater than or equal to 25. So we start from 25. We go 25, 26, 27, and so on. And it does not tell you the ending number. So we use the 3 dots to represent that the list just keeps going on forever. Now this one is the x such that the x belongs to the natural number, and another condition is that x is even. So remember that the natural number stack with 1, 2, 3, 4, 5, 6, 7, and so on. But we only take the even number, right? We want the even number. So we take 2, 4, 6, 8, and so on. So 2, 4, 6, 8, and then the 3 dots. No odd number. Okay. So this is the summary for the inequality notation and the set. This is a less than, and this is a less than and equal. So you can include the endpoint and so on. The same thing here. Now, another example, representing the sets of natural numbers. Now express each of the following sets using the roster method. This is the set of the order x such that x belongs to the natural number and x is less than or equal to 100. So we stack from 1, 2, 3, 4, 5, the 3 dots up to 100. We want anything less than or equal to 100 inside the natural number. The second case, we want x to be the natural number and they are between 70 and 100. So we stack from 70, 71, 72, and so on until 99. We are not having the equal sign at 100, so you don't want to include that 100 in here. Okay, another definition. We have the cardinal number. So the cardinal number of any set A, we use the notation n of A. So n, open A, close the parenthesis, is the cardinal number. The cardinal number is telling you the number of the distinct elements inside a set A. Or you can read up this way, n of A. Now, when we are counting the distinct elements, repeating elements do not change the value of the cardinal number. So for example, inside this set we have 1, 2, 3, 4. We have 4 elements, so the cardinal number is 4. We only have 1 element, so just 1. Now this one C, we have 13, 14 up to 23, so we have 11 different elements. So the cardinal number is 11. The next topic is about equivalent sets. Now the definition of equivalent sets is when set A and set B contain the same number of the elements. Or in other words, the cardinal number of the two sets, they have to be equal. So for example, Set A, X, such that X is a vowel. We know that it has letter A, E, I, O, U. Now this is a set of a natural number between 3 and 7. So we have 3, 4, 5, 6, 7. So the cardinal number of set A is 1, 2, 3, 4, 5. And the cardinal number of set B is also 5. So they are equal. Each element of A can be paired with exactly one element of B. And each element of B can be paired with exactly one element of A. So they are equivalent. Now, this is a one-to-one correspondence and equivalent sets. Now, we have to be very careful. If set A and set B can be placed in a one-to-one correspondence, then A is equivalent to B when the cardinal number is equal. However, they are not one-to-one when the cardinal numbers are not equal. Okay, try another example. Determine if the sets are equivalent. We see that set A is a set of 5 countries shows here: Zambia, Colombia, Poland, Italy, and United States. Set B is a set of the average number of years women in each of the countries prefer men who are older than themselves. Are these equivalents? Are these sets equivalent? And they explain. Now, we know that we have 5 different countries, and set A, we list the 5 different countries. However, the woman here, the number, the preferred age difference in the women, 4.2, 4.5, 2.5, and 3.3. Now 3.3, they are repeated, so we just take one value. Therefore, set B has only 4 numbers, and set A has 5 different elements, so they are not equal. They are not one-to-one, so that's why the two sets, they are not equivalent in this case. Set A has the cardinal number of 5, set B has 4, so they are not equivalent. The next one is a finite and infinite set. Now, set A is a finite set if the cardinal number of A is equal to 0. That is, A is the empty set. Or the cardinal number is a natural number. So that means a finite set has a cardinal number in which we can count 0, 1, 2, 3, 4, 5, and so on. We call the set to be an infinite set if we cannot count how many elements are inside the set. Equal sets. This is the last definition. Now, set A and set B, they are equal, means that set A and set B contains exactly the same elements. So set A has the same materials, set B has the same materials, and the order does not matter as long as they have the same elements. And we use the statement A equal B to represent set A and set B, they are equal. So for example, determine whether the sets are equal or not. 4, 8, and 9. And the other one, 8, 9, 4. Okay, we have 4. This also has 4. We have 8. This also has 8, 9, and 9. So we have the same thing in both sets, even though the order, they are not in the correct order, but they do contain the same things from the left set and the right set. So in this case, they are equal. So true. Now the next one is false because the right set has the element of 0 and we don't have that for the left set here. So they are not equal. So that's false. Okay, so that is the end of section 2.1.